Hey guys, I hope you're doing well. So this is going to be talking about at least the introduction into lab 7 here. So the first thing I want to do at least is to go over a couple things pretty quickly, at least in the math part, and then we'll get to the lab part. I'm going to kind of walk you through an example of kind of how to do things from step by step, kind of going through. So what I want to do is I'm going to share my screen here, kind of show you a whiteboard that I'm going to write on. And what I'm going to talk about specifically is I want to try to find, let's say I want to try to find the integral x squared y to the fourth dA of over this region D here. And this region D here is the circle, the unit circle. So a couple things to remember here. What you always want to do if you can, if you don't have access to something, right, like Mathematica, is to kind of draw out your region and to kind of just understand where you're integrating over. So let's kind of think about what this means physically first, right? This means that I have a function x squared y to the fourth. It's some function that has some z coordinate. I give you an x and a y, you give me a z. And this integral basically asks the question, if I'm just trying to plot this over this region xy, I plot this surface, and then I kind of shine, from the top here of f of xy, I shine that down, and I kind of make that volume, basically, it's kind of the net volume from that surface on the top to the xy plane. It could be the net volume because it could be negative as well. So you might have to be just a little bit careful if f of xy goes down. So what we're going to be mainly working on in this lab, a lot of this is going to be coming up with, the limits of integration sometimes and trying to figure out how we, input that into Mathematica. So there's a couple different ways that I'll show you here of how to do it. At least the first off, let's assume that I have Cartesian coordinates, right? And I want to try to figure out how to do this. So the goal here, when I have a general region of integration, and I'm trying to, figure out how to find this, right, is to kind of remind ourselves, okay, well, I'm going to first off assume that, let's assume I'm going with respect to y first, okay? Which means that I want to draw arrows going straight up. Okay, something like this here. Right. Arrows going straight up. Okay. Now, if I was going with respect to x first, I'll be drawing arrows going horizontally. And you could do that here too, because these are both type 1 and type 2 regions, especially this circle here. So you might, you can either do either. I'm going to go with respect to y, at least at the outset here. So what I'm going to now do is I want to see where I always enter the region from. As you can note here, I'm always entering the region from the bottom part of the circle, and I'm always exiting the region here. I'm always exiting the region from this top part of the circle. Okay, I'm always entering the region from blue, exiting the region from green. And so what I can do here is, if I want to figure out the equations for the bottom and upper, the lower and upper limits for y, right, what I can realize is that this circle is x squared plus y squared is equal to 1. And if I want my limits of y, I would like to solve this equation for y. Right? I want y equals something of x, right? I want these to be functions of x if I can. And if I do that here, right, doing this out, I'll get y squared equals 1 minus x squared. And then I take the, square root, and I get I get plus or minus the square root of 1 minus x squared. Now, I have two parts of this. I have the plus and the minus, right? So what does this say? Right, I have this bottom part is actually negative 1 minus x squared. And this top branch is 1 minus x squared, right? And so because of that, I can kind of separate this circle into two branches, right? I have this bottom part and this top part. So I know that y then can be bounded below. I see I'm entering from the blue part, which is the negative branch. And I'm exiting from the part of the top branch, so the square root of 1 minus x squared, something like that. And then lastly here, what I do is I now figure out my x bound. So where's x going from, right? X, the lowest bound of x and the highest bound of x. As you can see here, the lowest bound of x is going to be negative 1. My highest bound of x is going to be 1. It's very important that you remember here, when I'm creating my limits of integration, very important that at least one of your limits of integration is all constants, your last limit of integration, right? I have integrated out y. I have no more y after I've done this first part here, right? And now I just have in terms of x. So this needs to be a volume. I need to get an answer to it, right? Okay, So with this in mind now, I now have this integral, right? And I can rewrite this integral now if I wanted to formally rewrite this. And I could write this integral now as the integral, this integral from negative square root of 1 minus x squared over the square root of 1 minus x squared from negative 1 to 1 of x squared y to the fourth, integrated with respect to y first and then with respect to x. And this is my integration here. Now, how would I go about doing this in Mathematica? Right? I have this, I can go ahead and try to solve this, explicitly, I could do that, but I can go ahead and have Mathematica do it. Now, how would I go about doing that? Well, what I'm going to do instead is I'm going to use the integrate command. Okay, and this is something you've probably seen in, regular math courses, right? That you've seen in the past. You've probably done some integration with Mathematica, but this time we have double integration. So what you do usually, I'm actually going to do something a little bit different, is I'm going to define my function inside, which in this case was x squared times y to the fourth. Okay, something like that. So I've defined my f, and now I'm going to integrate f of xy. I now have to tell Mathematica what my x and y bounds are. And if you remember back what I just did, I integrated y first and then x. So if I'm integrating with respect to y first and then x, you need to write it like you do, like it looks like actually in the limits of integration. So if you see, going back to this really quickly, if you see here, this first limit on the left-hand side is negative 1 to 1. The second limit here is negative square root of 1 minus x squared square root of 1 minus x squared. That's dy and then dx. You want to write it just like this. You want to write it actually starting from the outside and going in. So in order to do that here, what you want to do then is, let me share this screen with you again. I'm going to go, x goes from negative 1 to 1. And y will go from negative square root of 1 minus x squared and square root of 1 minus x squared. Like that. Making sure that I tell it to say, what does this tell this, right? What does this actually tell the person, right? What does this say? This says, okay, I am integrating this function f of xy. The first thing I'm doing, making sure you use the curly braces, the first thing I do is I'm integrating with respect to y. I'm going from y, my lower bound, to my upper bound. And then I'm telling it, okay, go x from negative 1 to 1. And if I go ahead and run this entire thing, integration sometimes takes a little bit of time in Mathematica, so don't be too scared about that. It sometimes just takes a while. This is kind of how you get it. So you get this output. Now, I want you to be very careful here. If I had accidentally flipped these, and you're like, oh, will that matter at all? And the answer is yes, because I get an x here. I shouldn't be getting variables, right? Because this should be a number. It's a volume in this case. So be very, very careful that this is incorrect. What you should think about always is your innermost integral here. Your first integral that you do should be the last one that you write. Okay, and you should kind of run from that way. This is going to be the important thing when you go for this lab, especially using integration. As well, we do have, converting to polar coordinates here sometimes. And as you can kind of see, going back to this really quickly, you can come back to this later if you want to work with the first couple parts, and then come back to this video if you want to start to do a polar coordinates. That's totally fine. But I'm going to talk about polar coordinates here because we can actually do this a little bit easier with polar coordinates. So polar coordinates, right, allow us to really describe this circle much better, because I'm just trying to figure out my limits for r and theta. And what's nice here is r, if I want to redraw this circle, let me just redraw this circle here. Something like that. If I redraw this circle here, and what I could do instead is say, okay, well, my r here, r is the radius, right? So I'm starting at this middle point here always. This middle point, the radius at 0 is always that, right? This is always 0. So my radius always starts at 0, at least in this case, because 0 is in my radius. If that's not true, right? If this is, if the origin is not in your domain, you would not have 0. But then what we do is we go outwards. We draw arrows going directly outwards. And if you see, every single time I'm exiting from my domain here, I'm exiting from this circle. And that circle has a radius of 1. So what's nice here is that the radius will just go from 0 to 1. Okay? And then similarly here, we have a full circle. So again, this is 0, this is pi over 2, this is pi, this is 3 pi over 2. And as you can see, I sweep through the entire circle. If I sweep through the entire circle, that means my full circle is from 0 to 2 pi. And what's nice here, as I hope you'd see, is this is actually a polar rectangle. Because why is that? A rectangle only happens when I just have constants, right? If I have a triangle, that's not a polar rectangle. If I have a circle, or just not a rectangle, just general. If I have a circle, it is a polar rectangle. That's how we actually write it, because I can describe it with 2 variables with only constants. That's what we consider a rectangle. Now, just as a reminder, what do we have to do to convert it, right, to a polar coordinate? So if I have something like this, f of x, y, dA, right, what do I have to do? Well, I exchange my x for r cosine of theta. I exchange my r for my y for r sine of theta. And then I have to be very careful, because what I usually do is I multiply it by r. This now allows me to polar coordinate shift. This shifts the coordinates to where I want to be, in dr or d theta. You can go in any direction you want. Usually you'll do r first and then theta, because r will sometimes be dependent on theta. Theta will very rarely be dependent on r. That would be kind of brutal in a lot of problems. So the big things to remember, x becomes this, y becomes this, that becomes that. Now, you might say to yourself, well, in this problem, right, we could actually do this pretty quickly, because I would just go from 0 to 1 and 0 to 2 pi. In this function up here, I would just replace x with r cosine theta and y with r sine theta times r sine of theta to the 4th, dr d theta. Now, what's nice in Mathematica, and this is something I show in the lab and I kind of explain in the lab, what's nice when I do polar coordinates, what I can do instead is instead of having to actually go through, like you might initially go, okay, well, what I'll do instead, right? What I'll do instead is I'll name this now r, and you can use t if you wanted to. This becomes r times cosine of t squared, you know, something like that. And this becomes r times sine of t to the 4th. And then you would go, okay, well, then I'm going to integrate this, right? Then I'll do integrate f of rt, right? From r going from 0 to 1, theta going from 0 to 2 pi, something like that. You might say to yourself, okay, that's a way to do it. And it absolutely is. It's totally okay. It's absolutely okay to do that. But what's important to note here, oh, I forgot to multiply by r. Have to do that. This is actually really important. Good thing I messed up. You have your function here, but you have to now multiply by r, right? Because I've now polar coordinate shifted. This is really important because we didn't get the same answer. I was kind of wondering why that didn't happen, right? Because of what we did. Now, another way to do it, and actually the way I would suggest doing it, instead of going through this whole process, this is pretty tedious to go through this whole thing. It really is. It's really too complicated. Mathematica can do this for you. So what you can do instead, so I'm going to actually copy this. And what I'm going to do is I'm now actually going to say, okay, x here is really r times cosine of t. And y is really r times sine of t. And what I'm telling Mathematica here is say, every instance of x that I see, plug in r cosine of t. Every instance of y that I see, plug in r sine of t. And then multiply this entire equation by r. And again, I'll have my same exact limits that I just wrote down there. And so this now should give me the same exact answer. And these do. And so what did I do here? A couple things to remember. One, x is r cosine of t. Y is r sine of t. I'm telling Mathematica to do that. I don't have to go in and do this whole process down here. I don't have to do that. And you shouldn't. I actually like it this way because it's just subtler. And it's something that we'll see much in the next couple of labs. It's actually a really important concept. Make sure you multiply by r. It's a good one. and you have r from 0 to 1 and t from 0 to 2 pi. If these are all constant, does not matter which order we integrate in, right? So you can do either one. In this case, I've actually integrated theta and then r. You can go opposite way too. It'll still be the same thing. So let me just at least talk a little bit if I have any things about the lab that I want to just discuss here. That's at least the basic ideas. Making sure that you know how to just do that. Again, I did this top one for you up there. Making sure that you do the outer one first and then the inner one, right? You have to write it exactly as you see it in the integral. Making sure that computing these double integrals, you know, understanding why you're allowed to separate here, make sure you can explain that as a comment. Make sure you understand the geometric interpretations here and making sure that you understand what that's happening. This whole part, this part right here is actually pretty cool. It's exercise 4. This allows you to visualize and try to figure out what kind of domain you're actually in. Just come up with the limits of integration yourself. So make sure you follow this whole setup here, and to see what they're actually doing, definitely go through that first to make sure you fully get that. Then we go to polar coordinates and think about this. In this one, we want to try to go a couple different ways to use polar coordinates, to use a Cartesian, to use polar, and to use something that's like symmetry here. Think about the idea of volume in the terms of the interval, right? That's the idea. And then lastly, this last part here, you can try to, this is actually a really cool problem and something you should do by hand to figure out these limits, to go backwards. So remember, you can kind of work backwards here. You know what x is, the limits of x, you know what the limits of y are. So you can actually go ahead and try to draw those out and write those out. That's actually something that I would suggest, you know, really thinking about and trying to come up with. So write that by hand, draw it out, and try to convert it from Cartesian to polar. There's also this function called n-integrate. Integration is very tough in coding. So, and it's very tough, especially symbolically for Mathematica to do sometimes, and sometimes impossible. So instead what we would do is can use n-integrate to get a really, really nice approximation of it in like 1/10 of a second. And I've seen integration sometimes run for 15 minutes and no output gives you. So n-integrate gives you an approximation in seconds. It's not a really like a rational number. It's not really anything nice most of the time. It's just usually a decimal, which is still good for a lot of the process that we do. Okay, so I think that's it. I'll stop there. That was a long one, I know. I just wanted to kind of at least talk to you about that. You can come back to this individually if you want to throughout the lab. Let me know if you have any questions. I'll be around. So I hope you're doing well, and I'll talk to you soon.